We are looking at the normal distribution in this video, and I expect you to have looked at lecture notes 11, dealing with both the normal distribution and the standard normal. In fact, this video will mainly concentrate on the standard normal. Basically, the assumption will be that we don't have this luxury of just going to Excel every time and finding probability based on this command here, this norm.dist. If we have that, if it's in your calculator, that's great, and maybe in the future we should just expect that every student has that ability. But we're going to spend time on making sure we can read the z table and how to standardize an x value to a z. I just want to point out here that obviously probabilities will change. So I'm looking at the probability that x is less than or equal to 15 units below the mean. So right now the mean is 85, so it'd be 70 in this case. So 0.0993. So that's with a standard deviation of 11.667. And I found that using this command here. And then greater than would just be 1 minus that command. So let's change the standard deviation, and the way I have it here, the mean's going to change too. But since I have 15 units below the mean, that the location doesn't matter so much. So we now have the standard deviation smaller, and so obviously then the probability changes. Okay, so let's assume we can't use this. Let's assume that we're not experts at integrating the probability density function for the normal distribution. So what we have to do then is use something called the z table that's in the Grosvenor textbook, and it's used so much that it's not only in the appendix, but it's also in the inside back cover of the textbook. And basically what this is here is a standard normal distribution. So these are our standard normal values, okay, for a distribution in which the mean is always 0 and the standard deviation is always 1. So first thing we got to figure out is, well, how do we get to that? How do we get something described this way to a z where the mean is 0 and the standard deviation is 1? Well, hopefully you saw in the notes that that's just taking the difference between a specific x value. So say we want to take the probability x is less than or equal to 80. Well, if I know the mean is 100 and the standard deviation is 20, then my z would be the difference between 80 and 100, so 80 minus 100 divided by 20. So z is the number of standard deviations this given value is from the mean. So in this particular case, it would be a 1 standard deviation below, so that's why it's a minus 1. Okay, so that's how I standardize. Okay, and it doesn't matter whether this was 100 for mean and 20 for standard deviation, or 200 and 100. Okay, we can come up with a z value based on that. Okay, so let's just go back to the mean of 100, standard deviation of 20. So under that scenario, we're talking 1 standard deviation below the mean. So what is the probability of getting an x less than or equal to 80, or equivalently a z of less than or equal to a minus 1? Well, what we will do here is then, this is the z, so we need to look for a minus 1. Well, there's no minus 1 here. There's no negatives at all. Well, it turns out that because we have a curve like this, if we know the area between 0 and 1, we know that that's the exact same area between 0 and minus 1. So it's symmetrical, and works just fine. So Grosvenor has given us a table where we kind of have to use our imagination a little bit Other textbooks give us the whole thing. They go from, say, a minus 3.4 to a positive 3.4, and they give us cumulative probabilities all the way through. Well, Grosvenor says, you don't need that. And other textbooks as well. And so they just want to put it on one single page and say, and give you the upper half. So if we look up 1, we get 0.3413. Okay, now that's the area between 0 and minus 1, or 0 and 1, but we're dealing with minus 1, so let's pretend this is minus 1 here. So that's the area between 0 and minus 1. Well, I want the area below minus 1. Well, before I show you that, the other thing is we know that this whole area here is equal to 1. Okay, different 1 than what we're dealing with in terms of the z. So the area is equal to 1. And so if I split this in half, it's symmetrical. This area on the left-hand side is 0.5. This area on the right-hand side is 0.5. So always remember that. And so to get the area that represents z less than or equal to a minus 1, I take 0.5 minus the 0.3413. Okay, so the probability that x is less than or equal to 80 is 0.1587. Okay, and then probability x is greater than 90. And as you go through this, I think it would help if you drew the bell-shaped curve and then shaded in what you were trying to find, and then figure out, am I to the left of the mean or am I to the right of the mean? Well, I'm still to the left of the mean here, but now I want above. So I've got 90, when it's standardized, becomes 0.5. So 90 minus 100 divided by 20 gives us minus 0.5. So I look up 0.5, since I don't have a minus 0.5. I look up 0.5. I get 0.915. So that's the area between 0 and minus 0.5. Well, I want everything above that. So I've only got a portion of it. Now I need to add the right-hand side area, which is 0.5. So now I've got 0.6915. Okay. Now I've got two values. What's the probability x is between 75 and 110? Okay, so standardize both values. 75 standardizes to a minus 1.25, and 110 standardizes to a positive 0.5. So if I find the area between 0 and minus 1.25, that's right here. Okay, and then add that to the area between 0 and 0.5 right there, then I should get 0.5858. Okay. Probability x is less than or equal to 115 standardizes to a 0.75. So again, draw your curve. You can see that 115 is above the mean. Okay, so 0.75 is above the mean as well, and so you want the area below that. This is probably the easiest one because it's a pure cumulative probability. So you go to 0.75 here. So 0.2734 and add 0.5, the entire lower tail. Okay, so 0.5734. And then finally, probability x is greater than or equal to 142. That standardizes to a 2.1, a z of 2.1. So 142 is 2.1 standard deviations above the mean. What's the probability z will be greater than or equal to 2.1? So look up 2.1, that's 0.4821. Well, that's the area between 0 and 2.1. I want the area above that. So 0.5 minus this number, then, so 0.5 minus the 0.4821 gives us 0.0179. Now you can go the other way. You can convert from probability to x. Since we know the z is equal to x minus mu divided by sigma, then we can find x equal to mu plus z times sigma. So we're just rearranging this formula here. Okay, so if I know the probability, I can find z, and then if I know the mean and standard deviation, I can then find x. So if I have a statement, probability x is less than or equal to some value such that it's, the probability is equal to 0.7823, what is x? Well, there's nothing 0.7823 even close here, because I've got to subtract out 0.5 here to actually get to the value that I want. Okay, so obviously I know I'm dealing with a positive number here because I'm looking at less than or equal to, and this is greater than 0.5. So what I want to look for is 0.2823, and that is right there. Okay, and so the z value corresponding with that area is 0.78. So that's why I plugged in 0.78 there, and then this is just this formula right here. So I'm taking 100 plus 0.78 times 20. I get 115.6. Okay. X greater than or equal to some given value is equal to 0.648. So again, you kind of have to, it helps to draw the curve and shade in what you're talking about here. So I'm obviously dealing with a value here that I didn't plug in right. There we go. Oops. Where I'm going to take 0.648 minus 0.5, so I'm going to look at 0.148, so 0.148, the value is 0.38, but I know it's got to be a negative here, okay, because I'm looking at greater than or equal to, and this is greater than 0.5, so that's got to put me below the mean, and below the for the z, below the 0. Okay, so I've got a minus 0.38, so x converts, or the probability that we're talking about, x becomes a 92.4. So the probability x is greater than or equal to 92.4 is equal to 0.6480. Okay, so these can be kind of confusing, but the more problems you do like this, the better, more comfortable you'll be. And then you can always check your answers. You're going to need to show me that you can read the table, because again, you may come across it in 263 or some other businesses. They might have quality control. They might just have a chart on the on the wall where you find probabilities real quick using a standard Z table. So I do want you to be able to read this. Some other calculations for greater than x equal to 0.1261. So now we're dealing with a value here that where we have to take 0.5 minus 0.1261. Okay, so we've got 0.3739. 0.3739 is not here. Okay, but it's pretty much halfway between, well, it is halfway between 1.14 and 1.15. So when it's real close to halfway, that's the only time I interpolate. So I went ahead and added a 0.005 here. Okay, and it is on the upper tail, so it's a positive number. So that converts to 122.9. So probability x is greater than 122.9 is 0.1261. And then this last statement, x less than x, or x is less than some given value equals 0.0678. So now we know we're on the lower end of the curve, and so we're going to have a negative number. But again, you're going to have to take 0.5 minus this to find the number that we need. So 0.4322. 0.43, this is a 0.4319, the next number is 0.4332, so the closest is 1.49. So that's, and again, because it's on the lower tail, we have a minus 1.49. So the x value then is 70.2. Okay, so hopefully that helps with using the z-table. Don't try to memorize when to add 0.5, when to not add 0.5. It really changes. It changes up, whether we're doing less than or equal to, greater than or equal to. Obviously will matter whether you're starting from probability going to x, or starting with x and trying to go to probability. So really, I think the best thing to do is to draw that bell-shaped curve and then try to shade in what you're trying to find, and then go from there. If you have any questions, let me know.